This video describes the 2D structural analysis of a steel concrete frame subjected to fire with the finite element software SAFIR. The frame is subjected to uniformly distributed vertical loads on the beam, as well as a horizontal point load at the top left corner, and below you can see what we will get at the end of the structural analysis, where we can look at the deflected shape of this frame modeled with beam finite elements. The frame is 3 meters high and 8 meters long. The columns are reinforced concrete sections of 300 by 300 square millimeter that were modeled in a previous video, and the beam is a W12 by 120 steel beam, also modeled in a previous tutorial. The fire that develops in the compartment is the standard ASTM E119 fire. On the right, you can see the model built in GmSAFIR, the graphic preprocessor. I am now going to switch to GmSAFIR to build the input files for the software SAFIR. In GmSAFIR, start by creating a new project, saving it in the folder of your choice, and naming the project 2D frame, use .geo extension, and open Cascade. To run the structural analysis, we need the .tem files that contain the data about the geometric properties of the section and the temperature of the section to be located in the same folder where we create our new model, which is the case here. We are now going to start with creation of the geometry. Select Geometry Elementary Entities, Add Point. The first point has coordinates 0, 0, 0, and we are going to prescribe a mesh size of 0.2. Second point is with a y of 3 for the 3 meters of the frame. Moving then to 830 0.2 and finally 800 0.2. This creates the 4 points we need to build our frame. We can close the window and press Q to abort. Now we are going to create lines, and we select first point 1 to point 2, next point 2 to point 3, and finally point 3 to point 4. It is important here to be careful in the way the lines are defined. Specifically, the starting point and the end point determine the direction of the normals for the line. We can visualize that by going into Tools, Options, and showing the normals and tangents. I defined the normal pointing up on the left, then right, and then right downward in order to have the fire oriented on the right direction when I assigned my TEM thermal sections to those members. We will show that later on in this video, but it's important to note that because we have three-sided fire exposure, we need to make sure that the sections are oriented properly. This concludes the creation of the geometry for the frame. Next, we will assign properties, starting with the SAFIR general data here. In problem type, change to Structural2D. Name the file 2dframe.in. We are not going to set a threshold to the max displacement. We can change the precision to 0.01. This is related to the criterion for convergence during the iterations at each time step. We can keep 2 gauge points along the beam elements. We want to consider thermal elongation. We want to run the simulation and print the results for 2 hours. There are different modes for the numerical strategy, and we can keep here a dynamic analysis with a pure Newton-Raphson approach. We consider the comeback with a minimum time step of 0.001. We want to run the simulation for 2 hours with a maximum time step of 128 seconds. If convergence is easy, SAFIR will accelerate. Here you have a number of options related to the results that you want to be printed in the output files. We are not going to change this. And this concludes the definition of the general input data. We will now define the model properties using the physical group, starting with the boundary conditions. Going to geometry, physical group, add, point, type the name support, and select the 2 points at the bottom of the columns, point 1 and point 4. Type E. The window changes and enables selecting the properties for the support group. Select block constraint, and we will block the 3 degrees of freedom, X, Y, and rotation. F0 means that the degree of freedom is completely blocked. It could also be left free, or we could use a user-defined displacement for the associated degree of freedom. Click Add Update to confirm, then close the window. We can check that the conditions have been applied by showing the blocks here. And we see indeed the 3 degrees of freedom blocked for those 2 nodes at the bottom of the columns. Next, we will apply the load. We want to apply a horizontal point load at point 2. We could define a physical group, but since here there is only 1 point, we can also simply double click on the point, set the property type to load on node, set the load function to fload. The function f1 would apply the value of the load that is specified at once at the first time step. With fload, we apply the load over the first 20 seconds, which sometimes helps for numerical convergence. Set the X force to 2000 Newton, no Y force and no moment at the node. Click Add Update. Next, we will apply a uniformly distributed load on the beam. This is line 2. We double click, set property type to uniformly distributed loads on beam, load function to fload, and we have here a Y pressure of minus 4000 Newton per meter. Click Add Update. And we can check that we applied the load as intended with the node load and dist beam load. Next, we will define the materials. Double click on line 2, property type, select new material definition. Set the material type to non-load bearing because we'll start by defining the material that was the sprayed fire resistive material on the steel beam, which has no mechanical properties. Select the material subcategory as insulation, and we are going to name this material SFRM. Click Add Update to confirm. Next, we will add the steel of the beam, so we change the material type to carbon steel. We use steel EC3EN. The yield strength at 355 megapascal is correct. We don't change it, and we set the name as Steel M. Click Add Update to confirm. We see that now we have 2 materials for this beam. We will keep on defining all the materials before assigning them. So now we will define the concrete. set the material type to normal strength concrete, select silicon ETC, which is a siliceous concrete with explicit consideration of transient creep. We can use some tensile strength, 1 megapascal, and we name it concrete M, add update. What I'm doing here is that I am defining all the 4 materials of the model. There are 2 materials for the steel beam and 2 materials for the reinforced concrete columns. I can define my new materials at any moment, even if now I selected the beam. I am not assigning all the materials to the beam. I'm just defining them for the model. So our fourth material is a carbon steel, but this time it is a steel according to EC2EN because this is for the reinforcement in the column. And this one has 500 megapascal of yield strength. We are going to use a hot roll class A, so I'm not changing any of these. And the name is rebar M. Add update. I can now close the window. I have defined the 4 materials, but I have not yet assigned them, nor have I assigned the TEM files. I'm going to do that now. So go again in the properties of line 2. I double click on line 2. In property type, let's select beam section type. We now have to type the name of the TEM file that contains the information about the cross-section and temperature for this beam. In our case, this is thermal steel.te. Next, I need to list here the materials in the TEM file. And it is very important to provide these material names in the same order as that of the thermal steel computation, because this is where I link the materials of the thermal analysis and the section to the structural analysis. In order to make sure I am listing them in the same order, I'm going to go back to the input file of the thermal analysis. Going into my work folder, I find the file thermalsteel.in. I open it and go to the end of this file to check that the materials are defined with the insulation SFRMM first and second steel M for the steel profile. I will just go back to GmSAFIR and type the name of the materials in the same order, SFRMM, press space, and then steel M. Click Add Update to confirm. So again here, I input the 2 materials that are used in the TEM file, and I input them in the same order as they are present in the input file that generated this TEM file, so in the thermal analysis file. Add Update. I can now close this window, and I will now define the properties for the columns. I could again double click on the lines, but since there are 2 lines with the same properties, I am going to create a physical group. So I go into Geometry, Physical Group, Add Curves. I will label this physical group as columns. Select the 2 columns, type E, and now I can define the properties for the 2 columns at once. Set the property type to beam section type. The name of the TEM file is thermal concrete.tem, and I have to input the 2 materials. Going to go back again and check how these were defined. I see that first I had the concrete and next the steel reinforcement. So back to GmSAFIR, I'm going to type concrete M space rebar M. Add update. Close the window and I want to check that the materials were properly assigned. I see here the legend for the concrete. I have for the columns the thermal concrete.tem with the concrete and then the rebar. And for the steel, I have thermal steel.tem with the insulation, then the steel. This is correct. Next, I'm going to assign mass because I am running a dynamic analysis. I need to assign mass to the beam finite elements. So I will double click to go back to the physical group for the columns. See when I do that, the two columns are selected. And for property type, I'm going to select mass on beam. I'm going to assign a mass of 100 kilo per meter to the columns. Here, I must specify that this mass is not translated into a load by SAFIR. There is no notion of gravity. Loads have to be specified separately. The mass is used in the inertia term in the dynamic analysis. Therefore, the specific value of the mass is not influencing the results except for the inertia term when there is a sudden large acceleration in the displacements, but the value is not particularly meaningful in terms of the mass. It stabilizes the equations during the dynamic analysis. Add update. We will now do the same for the beam. For the thermal steel, the beam mass on beam at 100 kilo per meter. This concludes the creation or the definition of the properties. Next, we have to create the mesh. I'm going to go into mesh, and this time for this exercise we are dealing with beam finite elements, so the mesh is 1D. Click on mesh 1D. I'm going to open the dialog box and I see that it is done meshing 1D with 71 nodes and 74 elements. I am satisfied with this discretization. If you are working with the demonstration version of SAFIR and that you have to limit the number of elements, you have the option to adjust the mesh size by going into option, tools option, mesh general, and change here the element size factor. Note that we defined an element size when defining the lines at 0.2, so this will also have an influence. It should be set to a higher value if you want to have fewer elements. This concludes the creation of the model. We can now create the input file, and it was done successfully here by clicking on this button. Now we have in our folder, you see the 2D frame. This input file looks correct. All the information is present, and you see that at the end I have 4 materials. I can always check that my materials are properly defined. So it starts with the concrete and the rebar. If I navigate to here the beginning of the element definition, you see that first SAFIR will go and read the .tem for the columns, the thermal concrete one. The first material in that TEM file is going to be the first material here in the structural input file, which is indeed concrete. And second, it's translated with second. So the second there is the reinforcement. It is indeed the steel reinforcement. Then SAFIR will read the TM file for the beam. The first material in this beam TM file, which I still have opened here. Okay, first material in the input file was the insulation. And this translates to material 3 in the structural file. If I go to the end, I see that my materials is 1, 2, 3 is insulation, so this is correct. Always a good idea to make those verifications, and you see that you can trace back which material is which by looking here at the TEM and the translate commands and going back to the input file of the thermal analysis, which of course generated the TEM. One way to run the input file is to double click on a SAFIR executable located in the same folder. and typing the name of the input file, SAFIR start. This simulation is going to take a little while, a bit longer than for the thermal analysis, which are very fast. Here we have a structural analysis with about 70 finite elements. The loads are applied over the first 20 seconds because I used a fload loading function. So the loads are ramped up over from 0 to 20 seconds. Then these loads are maintained constant and the fire continues. Of course, the heating goes on as determined by the thermal analysis and provided in the TEM files. So here we have a simulation where the frame is loaded and the temperature in the columns and in the beams increases over time. The simulation has stopped. You see that SAFIR created a .out file and the .xml file. The .out can be opened to visualize results. I am here looking at the .out file. It starts with a copy of the data file, the input, and as you move down, you will see lots of results at each time step. First, the criterion for convergence and out of balance forces, and then the displacements that are plotted at each node for the 3 degrees of freedom. This is a 2D structural analysis. And if we go to the end, we'll see that the simulation did not fail. The simulation reached the 2 hours with no failure. We can now look at the results in Diamond. I open this 2D frame.xml file. I can check the elements, support conditions, the applied loads, point load, distributed load. The local axis will give me the orientation of the cross section. You see here that the local axis X is always in the direction of the beam finite element, and the local axis Y is defined according to the right-hand rule based on this definition of the starting point and end point. So here Y is pointing outside of the compartment for the beam and the 2 columns. This is why I defined for this column the X, or the starting point, being node 3 and the end point being node 4, in order to have X pointing downward and Y pointing outside of the compartment. This is because the positive Y is the phase that is not exposed to fire in my thermal analysis. In Diamond, we can plot the displaced configuration, and looking at the end of the simulation, we see this increase in deformations. We can also increase the scale to visualize even better, to see that in this case there was no failure. We can also plot the bending moments in the structure. We can adjust the scale if we find that it's difficult to read there. Okay, so we see that initially under the applied load, we have lots of positive bending moment at mid-span of the beam, already for most of the span of the beam, but we do have continuity at the beam column connection. And as the temperature increases, and of course we have a temperature gradient because the sections are heated on 3 sides, so it creates a restrained curvature, and we have a negative bending moment that builds up due to this restrained curvature. And you see that now the beam is completely in negative bending. We can also plot deformations or other data. For example, here at node 38, 39 for beam 36, we can plot the evolution of the vertical displacement. You see increase in vertical displacement as the strength and stiffness of the beam decrease. Finally, we can also plot axial forces in the members. We see all this compression. So initially, compression in the columns and some compression in the beam, and the compression in the beam that will increase with the restrained thermal expansion from the fire. This is Diamond to visualize the result. This is the post-processor for SAFIR. This concludes this example on the use of SAFIR for a 2D structural analysis of a frame using two different cross sections, a reinforced concrete column and a protected steel beam.